Hello, everyone. Today we have a special session, Infoshare session regarding RAR FreeRTR project and a very exciting 5G UPF implementation. UPF stands for User Plane Function, and this is basically the component that routes user traffic between the radio access network and the external network in the 3GPP 5G architecture. Today we have two specialists with us. We have David Franco, who joined the Communication Engineering Department of the UPV EHU as a researcher in IT2 Engineering and Research on Telematics. Research laboratory in 2016. His research is focused on software-defined networking and network function virtualization applied to traffic engineering and secure communication system. We also have the chance to welcome Asier Atutxa. Sorry if the pronunciation is bad. who joined the same laboratory in 2018, and his research includes cybersecurity, software-defined network, and virtualization applied to industrial environment. David and Asier, the floor is yours.
Good afternoon to everyone, and thank you, Frédéric, for the introduction. As you said, we both are researchers at the University of the Basque Country in Spain, and we both participate in the work package 6-1 in the deployment of RER. We are presenting the ongoing project, the open source implementation of the 5G user plane function. This is the content of the presentation. So we will first introduce the concept of 5G and provide some highlights of its architecture. We will then continue with a description of the RER router. After that, we'll present and describe our UPF implementation and the scenario in which it is planned to be deployed, including a short demo video. And finally, we will highlight the most relevant conclusions of this work. I suppose most of you attending this presentation are familiar with the term 5G. The first 5G deployment were operated in 2020. Since then, the number of 5G subscribers has grown up significantly. In fact, according to the statistics, more than 4.4 billion subscribers are predicted by 2027, mainly due to the impact of machine type communications. We highlight two factors are the main contributors to this change. The implementation of internet protocols in machine type communications, and also the advanced manufacturing processes that offload parts of their functionality to the cloud. Okay, this is like the two current trends in this type of communications. This means 5G changed the concept of the user equipment, or UE, inside a cellular network. For example, in 5G, a user equipment was represented as a human who consumes standard content such as web pages or video streams. However, the paradigm in 5G is a bit different because services are evolving from human-centric to device-centric services, with millions of heterogeneous devices connected to each other, we have now not only humans, but also other types of devices communicating between them. Another important fact to understand the context of this project is the composition of the 5G market. Okay, the 5G market, as represented in this chart, is composed of a few tier 1 vendors. However, it is remarkable that the market is also opening its doors to new vendors that are growing slowly, but which are already providing more customizable and affordable products. Okay, so you can see that there are like Huawei, Ericsson, Nokia, Samsung, and ZTE are like the big ones, but we have also market for other let's say smaller that are also like gaining attraction in the market. Let me say that also that the problem with this is that most of these vendors are still have elevated prices that make these solutions unsuitable for most of the academic and research environments, which is like our main problem now. In general, a cellular or a mobile network is divided into two main parts, as shown in this slide. Okay, we have the radio access network and the core network. For example, in 5G, the radio access network is also divided into three main elements, which are here represented as the radio unit, the distributed unit, and the central unit. The radio unit, for example, converts radio signals into digital signals for its transmission over packet networks, and it generally handles low physical layer functionalities. The distributed unit is a software deployed close to the radio unit and usually on commercial off-the-shelf equipment. It performs baseband processing functions. And finally, we have the central unit that is responsible for non-real-time protocol stack. Okay, this division, let's say, is like kind of new in 5G because in previous generations, everything was more monolithic. Then inside the 5G core, we have the 5G core that is a bit different from the radio access network. It follows a service-based architecture, which means it is a compilation of interconnected network functions instead of being also a monolithic component as it was in previous generations. Each network function is self-contained, independent, and the most important thing is that it exposes services through well-known interfaces such as REST, audio, and QUIC. Network functions are divided into control plane and user plane functions, as shown also in this slide. The control plane functions perform operations such as authentication and mobility management, and they are usually virtualized. Okay, so they can be deployed in cloud platforms such as Kubernetes. And then the user plane functions are responsible for the routing and forwarding. They have more stringent requirements and usually require a specific hardware. Okay, so for example, the UPF that we are addressing is the responsible for forwarding the traffic between the users inside the 5G network and the external data networks, and therefore a router might be suitable to deploy such function. We focus now on the 5G core, as our project consists in implementing a UPF, which is part of the 5G core. We are going to see now different alternatives of the 5G core deployment. First of all, the 5G containerization and distribution, which is one of the 5G use cases or types of deployment, let's say. As previously explained, the modular design of 5G network functions makes them suitable for their virtualization or containerization. So in current 5G deployments, network functions are provisioned as standard containers in a cloud service platform, so they can be distributed at different locations to optimize the resource utilization, for example. But not all the configurations are possible or are optimal. For example, if two network functions exchange large amounts of traffic or they require low latency response, placing them in remote locations will even degrade the service performance. So you need to take care about all the different situations. Then we have the 5G slicing, which is also represented in this slide, and another example of the 5G deployment, which is a concept in which is a kind of segmentation of the 5G network to isolate the traffic and apply different security and routing policies if necessary to that traffic. In this case, some network functions are or can be duplicated and only shared in one slice, and other ones can be shared among all the slices. A typical example is to have different slices to assign more priority to certain traffic, which is natively done inside a 5G network. Okay, so with all this in mind, our project focuses on implementing a UPF in RER. So RER is the key pillar, let's say, of this project. Okay, so RER is a production-ready router created for academia and research, and it is developed by GÉANT and fully open source. It provides command line interface to access multiple control plane functions, and you can customize the configuration also. The good thing is that RER routers support multiple software and hardware targets, and also the ability to provide specific data plane implementations. The most common ones are DPDK, or the most used ones, DPDK, XDP, and also Topino switches. RER provides the most used routing, forwarding, and tunneling functionalities. And the high performance provided by a RER router is probably its main strength. It has been tested at 100 and 400 gigs using Topino and Topino 2A6. So this means RER provides a performance comparable to any commercial equipment, such as the well-known equipment from Cisco or Aruba or whatever. And another advantage of RER is that it allows users to deploy their own control functions and also data plane algorithms. So this means you can easily implement new functionalities. Okay, so now I give the floor or the control to my colleague Asier, who will explain the implementation of RER and the scenarios.
Thank you, David. So recapitulating all the information we've seen with David, we see that there's an undeniable, it is undeniable that the expected status of 5G networks and subscribers will grow a lot in the next years. So we also saw that tier 1 5G vendors are slowly leaving place for other kinds of implementations and deployments, such as for smaller companies or open source alternatives, right? And we also saw that there are very excellent alternatives in open source, such as the RER router that David explained, which is developed by the GÉANT program. So in this context, we decided that it would be truly interesting to participate in the development of a 5G open source alternative, right? And taking into account that the virtualization nature of 5G, the network functions can be virtualized in any generic hardware, thanks to the virtualization, right? So there is no problem in that aspect. However, there is a hardware component by definition in 5G networks, which is the user plane function that routes the traffic from the subscribers to the internet. So that's where we decided to focus our implementation, which is in the UPF, using a router developed with RER or for RER, right? With the objective of achieving an affordable UPF system that could run in generic hardware and could be integrated in any virtualized 5G core, which are plenty of options in the internet. Okay. So with this in mind, we have a look at the UPF functionalities that must be implemented by the RER router. Okay. So the UPF has 3 main interfaces. Okay. Each one with different protocols that must be implemented and must be deployed and developed. So first of all, the M4 interface connects the UPF with the rest of the core network, okay, with the control functions, okay. and specifically with the session management function or the SMF. Okay, this communication uses the PFCP protocol, which is used by the SMF to send to the UPF the routing preferences and policies that must be followed by the router. Okay, so depending on the conditions and the traffic that is being routed, it has to act like differently, and that is organized by the SMF. Okay, so the SMF, in other words, installs routing rules in the UPF using the PFCP protocol. Okay, so PFCP is the protocol that we must develop for REN. Second, we have the N3 interface, okay, in which the UPF receives user data from the 5G base stations and the radio access network, and then the received data is encapsulated in the GDP version 2 protocol, which is used for the correct routing of data packets from the users to the UPF. So the GDP version 2 protocol is the one implemented in this interface, okay? And third, we have the N6 interface, which is the in which the UPF sends the data packets towards the data network, which is typically the internet. Okay, it can be any external data network. Okay, but it's typically the internet. And from this point, packets are decapsulated and routed using the regular IP. Okay, so at this point in our development of the UPF in RER, it obviously implements IP protocol, and it also implements the PFCP protocol, which we tested and it's currently working. And the implementation of the GDP version 2 is in an ongoing work right now. So therefore, our RER-based UPF is almost ready for deployment in any infrastructure. And that's what we're going to talk about right now, because for us, in our case, we plan to deploy it and test it in this scenario that we can see here in our slides. The infrastructure that you can see is called Smart Networks for Everything, which is our experimental infrastructure for network research in the Faculty of Engineering in Bilbao, in the University of the Basque Country. It is a large network that interconnects 3 distant sites at 10 or 100 gigs, depending on the exact link. And the 3 sites are the Engineering Faculty in Bilbao, the University campus, the main campus of the University of the Basque Country, which is in the Lloa, about 15 kilometers away, and the Advanced Aeronautics Manufacturing Center, the CFAA, which is about 22 kilometers away from Bilbao. So therefore, this infrastructure includes several points of interest for many knowledge areas. For example, computing, networking, advanced manufacturing, health, and that's why it is interesting for a deployment like this one. And it must be also noted that it is extremely interesting because the whole infrastructure is integrated into slices, which slices research infrastructure S3. And it is also well connected to other architectures, such as it has also a point of presence of GÉANT, and also another point of presence of REDIDIS, which is the Spanish NRED, the National Research and Education Network. Okay, so now we will check each one of the sites more in depth, okay? So first we see the first site, which is the Engineering Faculty in Bilbao, which is the main site where we work, which is where we are right now. And it has several computing nodes, as well as commercial and experimental 5G non-public networks, which we deploy experimentation bands to test our things. These systems include radio equipment, obviously, the core sensor networks, which are obviously the actual subscribers of the 5G networks that we deploy. And as a research entity, the site has all kinds of network analysis equipment also, which are like traffic generators, fiber testers, everything. And more importantly, what we are talking about right now, we also have P4 networks for experiments with multiple P4 switches of different manufacturers that allow us the testing of new functionalities or routing schemes. Also, just as a note, we also have, which is very interesting, also the quantum key distribution equipment, which you can see here in the slide, like here, which is a technology based on quantum physics that is used for the transmission and distribution of symmetric keys between two distant points for later use in cryptography. And we pair it with another QKD equipment in the next slide that you will see, which is the Advanced Manufacturing Center, Aeronautics Manufacturing Center in Zamudio, okay? Here is where our mechanical and industrial engineering colleagues work, and they test their technologies. And well, more or less here is where we help them with the networking issues and everything, and we work together with them in like Industry 4.0 projects, okay? Here we have experimental IoT networks which use LTE-M or narrowband IoT, okay? And we also have 5G deployments. We will also have in a near future indoor commercial millimetric wave networks, okay, in the next months. So we are looking for that. Yeah, more or less, that's all. We like what we mentioned in Bilbao. We have also the QKD equipment here, and we distribute and share encryption keys between both sides. So then we use those keys to encrypt or cipher all the information transmitted between both sides. Okay, so that's also an interesting idea. And finally, we have the third site, which is the Leioa site. Okay. The main campus of the university. Here we have a very big data processing DPC, a very big data processing center. And here is where we have the points of presence of GÉANT and the Spanish REN and Frédéric, okay? It is also, as it is also a big campus, it is a perfect place to establish an outdoor commercial 5G MPN, which we will have also in the next months. So after analyzing all the scenario and describing each of the sides of the smart networks for everything infrastructure, what is the role of our rare UPF implementation here, right? So our plan is to deploy the developed UPF in 2 sites, okay? 2 of the 3 sites. First, we want to deploy it next to our 5G core, which most of the times is deployed in our computing nodes here in Bilbao, okay? As it is the main site for this purpose. This core will manage the radio access network that will be implemented in the other site in the Advanced Aeronautics Manufacturing Center, making use of all the industrial IoT devices and monitor the advanced manufacturing processes also, okay? Later you will see that we have a video where we show all the processes, and you will understand it better later, okay? But we will use our UPF here in Bilbao with the core network, and the radio access network will be implemented in the Advanced Aeronautic Manufacturing Center. And the other deployment that we want to do is in the UPF that will be deployed in the Leioa campus, next to the points of presence of GÉANT and Frédéric. This way, we will be able to route the traffic to different data networks, depending on the purpose of the traffic, okay? And we will also fulfill our first target, which is to develop an affordable UPF, which will be used for academia and research, okay? And in our case, we will use this this deployment for experimentation with new applications in 5G, and also in semi-production environments with industrial data, which we will do with our colleagues from the Advanced Manufacturing Center. Okay. And now we have prepared a video. Well, we had prepared a video earlier, and I think this will help you to understand better how the whole infrastructure and different sites are interconnected and what we have in each site and everything. And there's also a small part where we show the configuration of the UPF in our RER router. Okay, but maybe we will jump first to the conclusions. Okay, just for logistics, because we can explain the conclusions and then change the presentation and go to the video and we can explain it there. Okay, we will also send you the video so that you can later see it offline or if you want. Okay, so as a conclusion, the main target of our work is to develop a high-performance user plane for 5G core networks using our open source implementation of RER router and to implement it in an experimental network, okay, which is our case with the infrastructure smart networks for the region. And looking at the future, we plan to finish the implementation, okay, as there are some parts that are still must be polished, okay, and we have to test them and do some performance tests and before getting it ready for production. And finally, it would be also interesting as a conclusion for us to focus on other 5G components that we work with in our normal jobs. So such as the session management function that we mentioned earlier, or even the non-3VP interworking function, which is the function, the control plane function that is used for the accesses that are not from the regular radio access network of 5G. Okay, so there are like other functions that can be also implemented in RER and could be also interesting for other 5G use cases. Okay, so with this set, we can see the presentation, the video. Okay, here you can see our infrastructure. Okay, so the first site that we can see here is the advanced manufacturing center. So here, for example, we have a brushing machine, which is used for making aircraft pieces. And here you can see, for example, I can pause the video. Here you can see the process from a close perspective. And this is all full of sensors, different sensors. Not all of them obviously are connected through 5G because most of the times these kind of companies prefer like cabled communications, but some of them are wireless, so this can be 5G or narrowband IoT. And we also have, well, our colleagues also have like automated machines here, as you can see. And to control all this and monitor all this information gathered by the industrial IoT devices, we have our access points of our 5G non-public networks. Okay, as you can see, we have like different deployments of antennas. Okay, here you can see the Bilbao University, the Faculty of Engineering in Bilbao, where we are right now. Okay, here is where we have our DPC, our data processing unit. You can see that it's a bit like messy because sometimes we change a lot of the configurations, but anyway. We also have 5G equipment that we can use in the experimental bands. And this, for example, is a device that we manufactured ourselves. Well, not the 5G module, obviously, but these are like experimental devices that we can use for our tests. Okay, so the idea is to deploy our UPF in the DPC, in the data processing center that we showed earlier, using any generic switch that we can use, like Tofino switches or whatever. And the other UPF would be implemented here in the Leioa campus. Okay, here you can see this is the biggest, the main DPC, the main data processing center of the University of the Basque Country. That's why it's much bigger than ours, and obviously it's better organized. And here we would implement our second UPF in this rack. You can see here, this one is our rack for this purpose. Here we have already a P4 switch connected to GÉANT, the GÉANT point of presence, which, as you will see now, it's like 2 racks away. This one is the rack from where the GÉANT point of presence is, and this one is our rack that we will deploy the EHU rerouter. Okay. And finally, like a brief part of the video will be focused on the implementation of the UPF in RER. Here you can see how we program. It's a bit messy, but for example, here we have our FreeRTR control plane of our implementation, and we have a mock program that sends. We have a small program that sends a PFCP message, for example, just to test it, and you can see it. So you can see that here there's a message, and the messages are exactly like the standard says. And well, anyways, that it works, and it's like any other typical router that implements the PFCP protocol. Okay. Now you can see the presentation, right? Well, it's just if there are some questions to go to the slide. Okay, so
we'll have one question.
Yeah, that's all. And now let's go to the questions.